All right, example 3 says an open top box is made by cutting congruent squares of side length x from the corners. So we can go ahead and label that. Of a 20 by 25 inch sheet of 10 and bending up the sides. So basically what they just told me is that without those corners cut, what the dimensions would have been. So 20 by 25. Okay. How large should the squares be to make this box hold as much as possible? So the other dimension you're probably going to be curious to know is these inner length and widths after the cuts were made, since that will make our new base of the box. So then if we cut out, in this case, an x from both ends of the 20, this would simply be 20 minus 2x. And then if we cut an x out of both sides of the 25, this is going to be 25 minus 2x. So just know that's pretty much where this is headed. And so we're going to go ahead and label that. So let's write down what we're going to optimize. And again, these should feel pretty familiar, like you did these in pre-calc. And we're going to have to use a calculator for this one, so a lot of you might be like, why even learn another way to do it if it still requires a calculator? Well, because there's a way to do it with calculus that, yes, you'll still need a calculator to solve the equation, but using those concepts of looking at critical points and understanding that that's where our slope is 0 for an instant, and thus it's a turning point. So here we're trying to optimize. It wants to hold as much as possible, so that's a sneaky way of saying to optimize volume. And there's no like second equation here, so to speak. It's more that volume is length times width times height, and we're just going to get them all in terms of x, which is not actually that difficult for us. So the length, I usually say it's the longest, so 25 minus 2x. The width would be 20 minus 2x. And then of course the height is simply x. I would say maybe we're going to think of the constraints when it comes to the types of answers we can have. So for instance, you wouldn't want an x value that's going to make your lengths negative, and it obviously shouldn't be 0 either. So you're looking for a positive number, but it can't be too big, or these lengths or widths might become negative. So that's kind of the hidden constraint here. It's not written as a separate equation. Okay, so yes, you're gonna multiply all this out, and you know what, it's gonna be okay. So in the end, you'll end up with 500x minus 90x squared plus 4x cubed. Use the area model if you would like. That's what I did off to the side. All right, so now we're going to take the derivative of this, and so that's simply going to become 500 minus 180x plus 12x squared. And we're going to find where this equals 0. Gross. Can we factor here? No. That's why you probably need your calculator. This one is not as pretty. So you would just use your calculator here to find when your first derivative is going from positive to negative on your x-axis. Okay, so if you were to graph it and just kind of zoom 6, you might not see this second one, but that's okay. Because that's going to be too big for us to actually have, since 10 was kind of the largest we could have as a dimension of x. So it's really this one here, and it's also more obvious because it's going from the positive side to the negative side. This is the first derivative graph, so where it changes from positive to negative is where our original function's changing from increasing to decreasing, and thus giving us that maximum. So then you can either do the 0 command or type in 0 into y2 and find the intersection, but either way, this is the one that we're going to be using here, 3.681. And then you'll state your favorite sentence. Thus, there is a max since v prime changes from positive to negative. And then we can actually answer the question. And this one's kind of nice. We don't have to like do anything with the answer because it just said how large should the squares be. So we can just simply say that we're going to cut squares of approximately 3.681 inches by 3.681 inches in dimension.